Removing vascular lesions. A pulsed dye laser emits light of wavelength lambda equals 585 nanometers in delta t equals 450 microsecond pulses. Because this wavelength is strongly absorbed by the hemoglobin in the blood, the method is especially effective for removing various types of blemishes due to blood, such as port wine colored birthmarks. To get a reasonable estimate of the power required for such laser surgery, we can model the blood as having the same specific heat and heat of vaporization as water. Suppose that each pulse must remove m equals 2 micrograms of blood by evaporating it, starting it at initial temperature T0, 33 degrees Celsius. Part A, how much energy must each pulse deliver to the blemish? So we're starting at 33 degrees Celsius, final temperature 100 degrees Celsius to vaporize 2 micrograms of blood. And we're given the specific heat of blood equal to that of water and latent heat of vaporization. The change in the temperature during this process will be from 33 degrees Celsius to 100 degrees Celsius, 67 degrees Celsius. The amount of heat that we have to provide, Q, is equal to mass of the blood that we're going to vaporize, specific heat of the blood, which is this equal to the specific heat of water, times delta T. And then we're going to go through a phase transformation from liquid to vapor, so mass times latent heat of vaporization. So this tells us that the amount of energy we have to supply is m times a specific heat of water delta T plus latent heat of vaporization. Okay, that's the amount of energy we have to supply. And now I want to note here that the change in temperature in the Celsius scale is equal to the change in temperature in the Kelvin scale. So if we calculate this, the amount of energy we have to provide is, so we have 2 micrograms, 2 times 10 to minus 6 grams, 10 to minus 3 kilograms. Specific heat of water, 4190 joules per kilogram Kelvin, times the change in temperature, 67 Kelvin, plus latent heat of vaporization, 2.256 times 10 to 6 joules per kilograms. So this gives us the energy each pulse must deliver to be 5.07 millijoules. Now let's look at part B. What must the power output of this laser be? What must be the power output of this laser? Well, the power output is equal to the energy that we supply during a pulse duration of delta t. So it's Q divided by delta t. So the power output is equal to mass of the blood, specific heat of water, delta T plus latent heat of vaporization divided by the pulse length, delta T. And if we calculate this, so the power output should be 5.07 millijoules, so it's 5.07 10 to minus 3 joules, divided by 450 microseconds, 450 times 10 to minus 6. This gives us a power output of 11.3 watts. So that's the requirement for this dye laser. Part C, how many photons does each pulse deliver to the blemish? Okay, so what is the energy carried by one photon? A photon is a wave packet. It carries an energy carried by one photon is equal to Planck's constant times its frequency, or Planck's constant times the speed of light divided by lambda, the wavelength. And lambda in this case is 585 nanometers. Planck's constant h is 6.63 times 10 to minus 34 joule seconds. The speed of light in vacuum is 3 times 10 to 8 meters per second. And the number of photons, n, capital N, the number of photons will be the total energy that we deliver, Q, in one pulse, divided by the energy carried per photon, which is Hc divided by lambda. That's the energy carried per photon. So this will be equal to Q lambda divided by Hc, which means the number of photons is equal to mass of the blood, specific heat of water, delta T plus latent heat of vaporization, that's Q, multiplied by lambda divided by Hc product. That's how we calculate the number of photons. If we plug in the numbers here, capital N is equal to the heat we provide, 5.07 10 to minus 3 joules, times the wavelength, 585 nanometers, divided by the Hc product, 6.63 times 10 to minus 34, multiplied with 3 times 10 to 8. This gives us, for the number of photons, 1.49 times 10 to 16 photons. Okay, so this basically is the number of photons each pulse delivers to the blemish. So that's the amount of energy we provide in the form of heat during one pulse. Now I want to also note here a useful calculation trick. If I note that Hc product divided by the electron charge, E, which is 6.63 10 to minus 34 joule seconds, multiplied by 3 times 10 to 8 meters per second, divided by the electron charge, 1.6 10 to minus 19. That gives me 1.989 times 10 to minus 25 divided by 1.6 10 to minus 19 coulombs. This gives me 1.243 times 10 to minus 6 electron volts times meters, which is 1243 electron volts times nanometers. So this is a good number to keep in mind. The energy of a photon, which is equal to Hc divided by lambda, is equal to 1243 divided by lambda given in nanometers and this is the energy in electron volts. Okay, so this is useful for quick calculations. Alright, so in this problem, we've looked at the amount of energy a pulse dye laser must provide with a wavelength 585 nanometers in one pulse period, 450 microseconds, in order to evaporate a 2 microgram sample of blood. And we're assuming the initial temperature of the blood is 33 degrees Celsius. So this energy is the energy that goes to the heating from 33 degrees Celsius to 100 degrees Celsius plus the phase change from liquid to gas. So it's mc delta T plus m capital L. So if we plug in the numbers, we find 5.007 millijoules. If this energy is provided in one pulse, the power output of the laser is Q divided by delta T, Q divided by 450 microseconds, that gives us 11.3 watts. And how many photons does each pulse deliver to the blemish? So that's in one pulse. The amount of energy that we provide is Q divided by the energy carried per photon, Hc over lambda. That gives us capital N, 1.49 10 to 16 photons. And finally, we note that this energy carried by one photon, Hc over lambda, if you plug in the numbers for H and C and divide it by the electron charge, we obtain 1243 electron volts divided by a wavelength given in nanometers.